We took a break. We're back from our break. Welcome. And we're going to start in with chapter 11, just because this is the most common type of hypothesis testing in the world. A t-test, we're going to do a 2-sample t-test for independent samples. So if you took high school statistics or some equivalent of that, you would have seen this. So I'm just introducing it now because this is some quick and easy stuff that we can do. It actually will follow its equivalent to doing a generalized likelihood ratio test, which is something that the book establishes. Let's see how this works. So we have 2 independent samples. I'm assuming I have continuous normal data here. And so then x bar minus y bar is normally distributed because any linear combination of normal is normal. The mean is mu x minus mu y, and the variance is sigma squared over n plus sigma squared over m because x and y are independent. So now, if sigma squared is known, then we can write out a confidence interval, no problem. If sigma squared is unknown, we have to do a little bit more work and use what's called a pooled sample variance. I had you guys check that this is unbiased. And then we pulled out this theorem which says that this test statistic is a t-distribution, and we actually proved it by recalling just basic definitions of what things are. So a t-distribution is a normal over the square root of a chi-squared, and a chi-squared, an example of a chi-squared is n minus 1 sample variance over sigma squared. These are independent because we're assuming that x and y are independent. So their sum is also chi-squared, and the degrees of freedom just add. So I defined x, and so I define z here, and u is chi-squared. Then this is by definition t, and all that we need to do is see that this z over square root u divided by n plus m minus 2 is this quantity given in the theorem here. So, and that's just a little bit of a calculation here. So that proves this theorem, and we see here that the standard error for x bar minus y bar is this pooled sample variance times the square root of 1 over n plus 1 over m. Good to know. And then we can write a confidence interval for the t-distribution in this way. Now, knowing all of that, we can do some hypothesis testing. So I'm introducing here what's called a 2-sample t-test. So your null is always that that the mean for the 2 samples are the same, and the alternative is that you can either have 2-sided or 1-sided alternatives. Alpha is your level of significance. We know from the previous theorem that assuming the null distribution is true, that this t here is from a t-distribution with n plus m minus 2 degrees of freedom. And so let's say we're doing a 2-sided test. This is our picture. We're going to reject here. So this is our rejection region. right? So we reject when the absolute value of t is in the tails. Equivalently, you can think of this that your confidence interval does not include 0. And this follows from the duality of hypothesis testing and confidence intervals that we discussed last time. Note that if n and m are large, that a z-test and a t-test are the same, because a t-distribution, when n is large and n and m is large, a t-distribution, this quantity, so this is approximately z n plus, so this is approximately z for n m large. And it's interesting to look in the book and see the proof that a z and t test is equivalent to a generalized likelihood ratio test. You would get exactly the same conclusion. The tests are equivalent. So take a look at that. And here, to end the day, we looked at an example of a one-sample z-test, which is a simple variant of a two-sample t-test. And